G'day. In previous videos we worked pretty hard to develop the theory of trigonometry and introduce the trig functions and their inverses. Today we're going to talk about actually solving trigonometric equations. We've run into trig equations a couple of times, but we've kind of avoided solving them. Our first job today is just to look at solving a simple example, and we're actually going to do most of the work in this section by just looking at a few examples. So suppose we want to solve the equation cosine of x equals 1/2. We know 1/2 is one of those special values that we can look up on our table. Here we go, cosine of x is equal to 1/2 precisely when x is equal to pi over 3. So we could say, just from this, that x is equal to pi over 3. Done, right? Another way of saying that is x is the inverse cosine of 1/2. That's what we worked on in the last section. The inverse cosine of 1/2 is pi over 3. But the trouble is we're not done. And we can see that pretty immediately by looking at a graph of cosine. Here's a graph of cosine. This is cosine of x drawn over a couple of periods. Here's where cosine is 1/2. And look, when I draw the line where cosine is 1/2, it crosses the function many times. In fact, it'll cross the function infinitely many times. And what we're going to do is concentrate on those solutions to cosine x equals 1/2, and we already see one of them. One of them is the one we've just talked about. It's at pi over 3 here. But there's also another one in the first in the first period. So we're going to concentrate on the zeros called the principal solutions that satisfy the equation in that interval between 0 and 2 pi, and then we're going to extrapolate to all of the other places on the cosine graph where cosine of x equals 1/2. So our first important idea is that the principal solutions to an equation, they lie in the interval from 0 to 2 pi. So our first important idea is that there are these things called principal solutions, and they're the solutions inside the unit circle in the first 0 to 2 pi, and we can see two of them here for this graph. We're going to find them. Let's draw the unit circle, and then we can mark cosine of 1/2. Cosine is going to equal 1/2 at precisely this midpoint here. Cosine is the x value. So at these 2 points on the unit circle, the cosine is equal to 1/2. One of them is the one we found using the inverse function. Remember, the inverse function will only return values that are between 0 and pi. Here's 0, here's pi. Inverse cosine, its range is 0 to pi. So we could only possibly get this point out of the inverse function, but there clearly is another point, and we can see it down here, and the symmetry suggests we've gone down as far as we went up, so we went down pi over 3 here, so this must be 2 pi minus pi over 3, and so this point is going to be, well, 2 pi is 6 pi over 3, so this will be 5 pi over 3. So there's our two principal solutions in this case. And we can see pretty clearly from the graph where those 2 points are. Here's one of them, 5 pi over 3, and the other one is here at pi over 3. Alternatively, we can see them on the unit circle. And so the unit circle is what we'll usually visualize them with. There are no other places where the cosine of x is equal to 1/2. In other words, the x coordinate of the point on the unit circle is 1/2. There are no other points between 0 and 2 pi. So those are our principal solutions. But there are clearly other solutions. I'm starting at pi over 3. I could move one full period ahead, and I'd end up at this point, which is 2 pi plus another pi over 3. So this next point is just a copy of our point from pi over 3, one period forward. Similarly, this one, if I move this point one period forward, it would end up here. I just extended the graph, and we're at this point. So this must be 5 pi over 3, moved one period forward, 2 pi. And we're going to get an infinite number of points like that. So the solution to this equation, the full set of solutions to our original equation up here, are going to be these points, but it'll continue forever. And in fact, it'll continue in both directions, because I equally well could take this point and subtract 2 pi. In other words, we're thinking about, if we view it the other way on the unit circle up here, I'm starting with this point, and then I'm finding the point that's coterminal to it, so is a full rotation forward, and another full rotation forward, and another full rotation forward. Or backwards, we could do a full rotation backwards. So if I started at pi over 3 and subtracted 2 pi, I'd end up at minus 5 pi over 3. And so we could continue writing this list out forever. But to abbreviate that, we're going to write it this way. We're going to say that the full set of solutions are given by pi over 3 and all of the copies of pi over 3 that are just 2 pi away from it. So one full rotation, two full rotations. So in other words, n is an integer. So it's 0 or plus or minus 1 or plus or minus 2. All of these integer n's are just doing full rotations from our starting point, and we've got two starting points, 5 pi over 3 and pi over 3. So that gives us an infinite number of solutions to this relatively simple looking equation, but we built them all by finding the principal solutions. Let's have a look at another. Our next example is similar. We want to solve sine of 3t is root 3 over 2. And to do that, again, we should look at the unit circle and find the solutions that are in the first interval 0 to 2 pi. In other words, find the principal solutions. So I'm going to imagine for a second that this tells me that I want to find the sine of theta is the square root of 3 over 2. Well, square root of 3 over 2 is about 0.7, so it's something like this. So we're talking about sine, we're talking about a y value, and so we're talking about points that are at about that height. And there are two of those, or there's 2 points where they cross the unit circle. One's in the first quadrant, one's in the second quadrant. Sine's positive here, and so we know we must be in those quadrants. And so we've got 2 points that we need to worry about. The first one is at an angle here, and if this is our theta again, the theta is, sine of theta is root 3 over 2. Going to our table, sine of theta is root 3 over 2 when that angle is pi over 3. So we've got an angle of pi over 3 here. We've got a second angle over here, also theta. And thinking about reference angles, this must also be pi over 3. This is pi, and so that one must have been 2 pi over 3. So our principal solutions, again, what I'm building here, are principal solutions to the equation sine of theta equals root 3 over 2. So the principal solutions are that theta is pi over 3 and 2 pi over 3. And so our full set of solutions for this equation, remember not the original equation, but this equation, our full set of solutions would have been theta is equal to pi over 3 plus any multiple of 2 pi. So plus 2 pi n, and also theta is 2 pi over 3 plus any multiple of 2 pi n. That would solve this equation that I altered from the original. But the trouble is that wasn't the original. The original equation had theta equals 3t. So I'm going to replace theta with 3t. So I'm saying that 3t must be equal to pi over 3 plus 2 pi n. And 3t must be equal to 2 pi over 3. That's the other alternative set of solutions. And I can then solve for t. So my solutions for t I get by just dividing through. Pi over 3 divided by 3 is pi over 9. And then we've got 2 pi over 3 n. And the other one is t equals 2 pi over, well, I'm dividing this 3 over, so it's 2 pi over 9. Plus 2 pi over 3 times n. And those two sets of solutions give me all of the solutions to the equation. And so we could start writing them out if we wanted, which would give us for different values of n. Well, if n was 1, we just have pi over 9. If n is if n is 0, we get pi over 9. If n is 1, we get pi over 9 plus 2 pi over 3. Here's where n is 2. Pi over 9 plus 4 pi. N is 3. Pi over 9 plus 6 pi over 3. In this direction, n is minus 1. So we'd have pi over 9 minus 2 pi over 3. And we'd have a similar set of solutions down here for the other equation, right? Because this set also gives some solutions. So it would be 2 pi over 9 plus some values, 2 pi over 3, and so on. In the other direction, we'd have 2 pi over 9 minus 2 pi over 3, and so on. So that we could get all of the solutions from this equation. What I've done in the last two examples, I want you to be looking at and extracting the big ideas that we're doing here. We're finding the principal solutions. In this case, I found the two principal solutions in the first two quadrants, and then I found the looping sort of solutions by adding multiples of 2 pi, but I also had to worry about the 3 inside the sine function. And so I imagined it wasn't there to begin with, I just called this theta. So these are ideas that we're going to have to use in all of the examples. There's no one way to solve trig equations, you just have to work with what you're given. Let's have a look at another. In this case, we want to solve an equation that involves 2 sine squared theta minus 3 sine of theta minus 2. And this theta here is the Greek letter theta, lowercase. And we want that to be 0. We want to find all the zeros, essentially, of that. Well, this is a polynomial. This is a polynomial. In fact, this is a quadratic in sine of theta. Because I can write this as 2 something squared minus 3 something minus 2 equals 0. It just happens that the something in this case is the sine of theta. So it's 2 lots of the sine of theta squared, and then 3 lots of sine of theta are being subtracted, and then we're subtracting 2. So we know how to solve quadratics. We can use the quadratic formula, or we can just look at that and factor it. In fact, if you look at that and factor it, if it helps, go to the side and think about this involving x. This would be 2x squared minus 3x minus 2 is equal to 0. And you can probably see that we can factor that pretty easily by having an x minus 2 here and a 2x plus 1 here. That will give us 2x squared minus 3x minus 2. And so we know the zeros of this function. In fact, in terms of polynomials, back to the sine functions, x is playing the role of sine, so this is 2 lots of sine theta plus 1. And then the other factor was just sine theta minus 2. And that's equal to 0. So I've just factored. Or you could use the quadratic formula. And all I've done here really is replace the x's that we had over here. This is a calculation from chapter 3. I've replaced them with sines when I've written it down here. Well, there are 2 solutions to this equation. Either this factor is 0 or this factor is 0. So let's look at each, one at a time. 2 sine theta plus 1 equals 0, this first factor. If that's true, then I can rearrange and say that sine of theta must be negative 1/2. If sine of theta is equal to negative 1/2, then we can draw that on the unit circle. We're literally back to doing what we did in the previous examples. Minus 1/2 is down here. Sine is the y value. So we're looking at the points along the unit circle that have y equals negative 1/2. So there are 2 such angles. There's one here and there's one over there. And we can use our, I didn't draw that well, we can use our, and so there are 2 such angles. There's one in the 3rd quadrant and one in the 4th quadrant. And so we just need to find those values. And we can do that pretty quickly by using reference angles, thinking about this as t prime. Well, I know that sine of t prime, just from our table, we know that sine of t prime is equal to 1/2 when the angle we're plugging in is pi over 6. So if this reference angle is pi over 6, then this total angle is pi plus pi over 6, pi plus the reference angle there. And so that total angle is our solution. And in fact, that's what we're calling theta in this problem. So theta, using these reference angles, theta could be pi plus pi over 6 is 7 pi over 6. That's one of our angles. The other one, well, the same reference angle, it's coming down this time, it's coming down this way. So we're pi over 6 short of 2 pi. So this will be 2 pi minus pi over 6. And so that gives us the 2 principal values, sorry, not reference angles, the 2 principal values, 7 pi over 6, and this one will be 11 pi over 6. And you can do this arithmetic and check. So there's our principal solutions for this first part of the problem. Remember, we've got another part of the problem over here. In this case, sine of theta equals 2. Well, that never happens, because sine of theta, the range of sine, remember, is just minus 1 to 1. So there are no solutions to this equation. Sine of theta is never equal to 2. So there are no solutions. So our only solutions are the ones coming from this first leg. And I'm really thinking about doing this as 2 different problems. I'm looking at this factor, looking at all the solutions that come out of there, looking at this factor, looking at all the solutions that come out of there. There weren't any. And so the total solutions are all of those combined. So the total set of solutions are just going to be these principal solutions and then the sort of copies by doing 2 pi rotations. So the total solutions, total set of solutions to this problem are 7 pi over 6 plus any multiple of 2 pi and 11 pi over 6 plus any multiple of 2 pi, wherein there, the way I'm writing it, is an integer. Okay, I hope this gives you an idea of how to proceed with some of these trigonometric equations. We'll talk more about it. Have a go at some problems.